Good morning, everybody. And first of all, I would like to thank the organizer to give me the opportunity to be here. Now I realize that it was not a nice idea to swap because now it seems that there is a sort of challenge. So RIM is the ideal confocal. I will try to demonstrate that ISM is the ideal confocal. Let's see at the end. So there will be a vote. So you raise your hand. No, apart the joke, so really nice presentation and thanks a lot because you anticipate a lot of things that I need. Okay, but yeah, today I'm not here only to talk about ISM, but I'm here also to talk about the concept of photo-resolved microscopy, and which leverage basically an almost not so new detector, which we call a single photon detector that we call a SPAD array detector. And I don't think that I will have time to show what we do, everything that we do with this detector, but I want just to show you at least a couple of examples. One of them is image scanning microscopy. So, but let me start from the beginning, a little bit from the motivation point of view. So yeah, as has been anticipated, I was working with Stefanel at the time in which, super resolution was really rising up. And so, for me, it was not a surprise, but I think that also for you, when I show this graph that basically tell you the number of publications in the last 30 years related to super resolution microscopy. So clearly there is an exponential trend. So that's also certified by the fact that in 2014, these three gentlemen got the Nobel Prize in super resolution. So, what has been done in the cause of super resolution in the last 30 years is really a lot. But maybe you will be surprised a little bit more by this slide. Okay, so that's exactly the same database. I took this data from Scopus. Instead of using the keyword super resolution, I used the keyword confocal. Okay, so yeah, confocal microscopy is still dominating quite a lot over super resolution. So, it's clear that maybe if I make a question, how many of people you are using confocal microscopy? Can you raise your hand? Okay, so I think that you reply to yourself about this slide. So for me, the reason of that is that somehow, first of all, confocal microscopy is a quantitative super resolution technique. You don't get only super nice images, but you get also really data. That's what you are interested in. You want to solve your problem. You don't want to have nice images. So it's a true quantitative imaging. And then on top of that, it offers a sort of unique combination of spatial temporal characteristics. So from spatial resolution to temporal resolution, from spatial range to temporal range. But let me go a little bit deeper on that. So first of all, I'm sure that you know confocal microscopy mainly for its ability to provide optical section. That has been discussed before, which tell you that basically you can navigate across your sample. You are interested in 3D life, not in 2D. Life is not flat, it's 3D. So that's a confocal microscope, you can navigate across your sample. So that's what we call the spatial range. So what about temporal resolution? Yeah, it's not maybe one of the fastest systems, but anyway, it still provide you a typical frame rate of hertz if you want a very large field of view, and up to different few hundred of hertz if you want a small field of view. So also the temporal resolution is not so bad. What about temporal range? Again, maybe you are interested in very long process that may last also minutes, day in the worst cases. So, and confocal microscopy with some trick can be used also for do lifestyle imaging. So at the end of the story, it has also a good temporal range. And then what for me, that I came from computer science, as I told you before, is a technique that provides me so many parameters about the sample. It's a true quantitative technique, especially when you go to combine with spectroscopy. For example, the fluorescence emission, when you measure the fluorescence emission of your sample, or when you measure the fluorescence lifetime of your sample. And so typically this kind of technique, this spectroscopy technique are so far better implemented in laser scanning microscopy. So what about resolution? Okay, yeah. Anyway, you get a sort of subcellular spatial resolution, which may be enough for many of your applications. So yeah, I may say that at the end of the story, it's not a bad system, but okay, that's the optimistic person that there is in me. But since I'm doing science, I have also to be a little bit pessimistic. And then what happens? So okay, spatial resolution, as we say, okay, we came from the world of super resolution, but confocal at the end of the story is not a super resolution technique. So we would like to get it better. Temporal resolution, okay, yeah, as I told you, you can get some kilohertz, but if you want to study molecular dynamics, how molecule, how small organelle diffuse, then it's not enough. So again, temporal resolution is not so great. Yeah, spectroscopy information most of the time are discarded. The sample in principle provide you, but you have a system that completely cancel out this information. Then toxicity. So we are using laser. So we should dose, we must dose pretty well this laser, otherwise we induce phototoxicity. And then optical aberration and scattering is another issue. So at the end of the story, it's good, but not super good. So at the beginning of my IT story, when I moved IT, I asked to myself, there is a way to try to, by the way, preserve this ability and try to a little bit expand all of them at the same time. So there is a way in which we can enlarge the temporal resolution, the spatial resolution, the information content. So I would like to really stay on the confocal microscope because it's a pretty well technique, but expand a little bit them all these properties. And so, and then what we thought that, but by the way, I mean, at least my opinion, this I found out that for me, how the images built in a laser scanning microscope and in a confocal laser scanning microscope, it's really, it's fundamentally limited. You lose a lot of information. So just to understand and to try to convince you about that, let's try to describe really fast how a confocal laser scanning microscope, in general laser scanning microscope, it works. So what you have, that is depicted a little bit a scheme of a confocal laser scanning microscope. So you have a laser, you use a typical high numerical aperture objective lens to focus your laser beam to excite the molecule in your sample in a diffraction limited region. Before has been mentioned that the size more or less is 300 nanometers. So all the molecule in this volume, which is a three-dimensional volume, by the way, that I typically call the probed region, the probed volume. All the molecules that are inside the probed region start to emit light. The same light is collected by the objective lenses and then projected by the Galvo mirror and some lenses into your photomultiplier. So the photomultiplier, what it's doing is basically collecting all the intensity that are in this plane, so integrate all the light that arrive here. That's a very important point. Here there is a sort of integration. So because at the end of the story, I end up with a single intensity value, which is changing time because the typical photomultiplier has a very high bandwidth, so it can be also the gigahertz. So, but anyway, it's integrating in space. Then there is a data acquisition system in your microscope that maybe you forget it. So there is a lot of electronic. That electronic, what is doing is integrating across the time. So for each pixel, because then you scan your beam across your sample, you record a single intensity value. Okay, so there is a lot of things that are happening here, but at the end of the story, for each position of your sample, you collect a single intensity value because you average across space and you average across time. Okay, there is something not nice. First of all, because if you see what this microscope is telling you is much more than a single intensity point, because you focus the light in a region which is small, but it's still a region. Okay, it's still space. And what you generate is an image here. But since you have a single element detector, you integrate across space these images. So that means that you are losing information. So every time that in physics, whatever, you average, except in the case of RIM, you average information, especially if there is heterogeneity. And clear is there is heterogeneity, there is an image, and you are averaging. You are canceling out completely. But what about time? It's the same. I mean, we are measuring fluorescence. There is a lot of phenomena, a lot of photophysical phenomena. And what we do, we simply integrate across time. We discard all this information. And that's what happened in a typical conventional laser scanning microscope. A photomultiplier and what I call an integrative data acquisition system. So, but we are losing information. It's clear that this is a fundamental limit. So it would be nice to keep all this information, to keep both the space and the time information. So, okay, let's try to think, okay, I want to keep the time information. So what I, for example, can do, instead of using an integrative DAC, I can use a time tagged DAC. So a system that is able to sampling at the gigahertz or anyway, photon by photon, my fluorescent signal. In this case, I could recover all the time information. But what about the spatial information? It's still a single element detector. So that means that anyway, I'm preserving the time information that in my system, my sample is able, and my microscope is able to provide, but I'm losing the spatial information. Okay, I can use a camera, a pixelated detector. Great, I keep the spatial information, but what about the temporal information? Again, camera, unfortunately, are limited in frequency, in frame rate. So up to a certain limit, I keep the time information, but not like they would like the time information that in principle microscope is able to transmit, that I'm talking about even picosecond or nanosecond regime. So yeah, at that time there was really, I have the motivation, but I don't have the technology. Okay, I was so lucky that I have the chance to work with the Polytechnic of Milan, sitting together and say, okay, let's try to do a detector that is able to provide what I tell you, that is able to provide spatial and temporal information. And we came up with this, what I like to call the first camera detector designed for photo-resolved measurement. Because what I ideally would like to do is to collect the light photon by photon with a different spatial and temporal signature. And that's exactly what my detector is able to do. So first, just I don't want to go into the detail of the SPAD array, which is the single photolavlular diode array, which is the name of this special detector. I like to say that are a synchronous readout detector. I will try to explain why in a short. I think that there will be a workshop about that. So if you are interested about this detector, we can talk later. So, but what is important to say, first of all, it's a small detector. It's only 5 by 5 elements, 7 by 7, 10 by 10, something, but very small. It's not a megapixel camera that you are typically get used in wide field microscopy. But it's okay if it's small, because anyway, I have to do an imaging of a very small region, so 300 nanometer in size, so I don't need a lot of pixels. But since I don't need a lot of pixels, what happened is that I can read the signal from this detector in an asynchronous way, so in a readout asynchronous way. So basically, every time that a photon is injected in one of these elements, there is a digital signal that is transferred to my data acquisition system. So I can really sampling the photon one by one in space. I can tell exactly where the photon arrive in this detector. So, and this is, I mean, one can think, okay, but since you have 7 by 7, why not to make it bigger, 500 by 500? Because you have to think that from this region, you get almost 2 megahertz of photon. So 2 million of photon per second. And for each of these photon, I have to register where it comes from and transfer to a computer. So if I have a lot of pixels, this operation is at the moment is impossible. Also because on top of that, I do not transfer only the information where the photon arrive, but also when the photon arrive with a precision of 100 picosecond. So transfer to 2 million of photon per second with a precision of 100 picosecond is a lot of data. So for the moment, this asynchronous readout detector forget to have much bigger. You need to start to introduce some averaging. Gating is a sort of averaging. But I want to have this data, because what I want to do is really a photon-resolved microscope, a microscope that is able to tag every single photon with a spatial and a temporal signature. So unfortunately, it was not enough to have this detector, but what we have to do, we need to develop a specific electronic for collecting this data. And the funny thing is that at that time, this electronic basically does not exist, or you need so many money. And then they decide we build by ourselves with an FPGA. So, but nowadays I'm happy to say that there are many companies that also provide up to more than 25 channel or 49 channel or whatever, a lot of different channels to make this time tagging measurement. But what is important at the end of the story, that I don't have any more an image, but what I have is a list of photons. So it's a sort of new paradigm. Okay, so I have a list of photons, and for each photon I know where it arrived from the sample, because it's a scanning system. It has this coordinate x, s, y, s that tell me where the photon arrived from the sample. I have also the detection position of the photon, because this is a detector, this is a pixelated detector, so I know where the photon arrived on this position. And then I know a series of temporal signatures, which are, for example, the photon arrival time with respect to a laser sync when I'm using pulse laser. That's very useful for the next part of the talk. Or I can tell you which is the absolute time of the photon with respect to the beginning of the measurement, or the beginning of the change of the position of the piezo, of the pixel, and so on. I have plenty of information at the single photon level, spatial and temporal. But what is an image? An image is an histogram. Okay? If you think an image is just a photon counting histogram in 2D. So I can always do this operation. From my photon-resolved microscope, I can always be the conventional images. But clearly I cannot go the other way around, because that's averaging. I'm throwing away information when I do this operation. Histogram is not good, it's an averaging. It's an integration. Okay, so I have this data set. So, and I mean, I like this slide because it's a sort of parallelism. So we know about single molecule mainly for this guy because we are working in microscopy and imaging, but clearly single molecule open a revolution in the field of biophysics. Because for the first time, you can get access to the information molecule by molecule. And the idea is now to move to a level down, get information photon by photon. Okay, so when we got this magic system, the detector and the data acquisition, we introduced in our laser scanning microscope. And basically we ran a, so it was a really nice moment. It was a sort of magic moment in the lab because we start to run a lot of different measurements to try to really expand all the characteristics of a confocal microscope. So I'm really happy that we was not alone because the other group in the world start to working on similar things. So in parallel, maybe they do not call photo-resolved microscopy, but the idea is exactly that. And also that company start also a little bit to support because basically they realize the potential and they start to introduce this type of technology inside them system. So obviously I don't have time to show all this technique, but I want to focus in a couple of them and especially in the one of image scanning microscopy. In this specific case, I will have my photo-resolved data set, and what I will do at the moment, I will discard all the temporal information. I will just keep the information where the photon arrive in my detector, okay? So I will leverage part of the information, but at the moment I'm not interested in all. So let me start to motivate it. That's a little bit a repetition of what has been already said by Anna. We'll go very fast. So again, when you think about a confocal microscope, you know it for this ability to generate optical sectioning. So basically, if you place a pinhole in front of your detector, you are able to reject the light coming from out of focus plate. So smaller is the pinhole, and better is the rejection of the autofocus light. So, but maybe something that you know, now you know because it's been already said by Han, is that if you close the pinhole, what you have is also a reduction of what we call point spread function of, or how you call it, sorry. Okay, point spread function. So basically what happened is you squeeze the region from which, the probable region from which you collect the light, and thereby your spatial resolution of the system increase. As you can see here, basically if you close the pinhole, what you end up is an enhancement of the full Vidal maximum of your point spread function of a factor of square root of 2. But as it has been demonstrated also by Jan before, that this means an enhancement of resolution twice because the frequency enlarge. So this is exactly what happened in a structural illumination microscope. This you can see also here from these images of particle in which you close the pinhole and basically you can better resolve the different particle that you have in your sample. But why? So I'm saying that confocal microscopy is a super resolution microscopy. But as been said before, so what happened is that unfortunately, when you close the pinhole, you do not only remove the out of focus light, but also remove the in focus light, the light that's coming from your in focus plane. So at the end of the story, you reduce the signal to noise ratio of your images. As you can see here, if now I take the same sample but illuminate it less because this is not able to provide me enough photon, what will happen? I end up in an image that is completely noise. So that means that when you sit in front of a confocal microscope, in principle, you are sitting in front of a super resolution microscope, but at the end of the story, you have to balance between resolution and signal to noise ratio. And most of your application, you have to sacrifice resolution to get signal to noise ratio. So okay, how I can solve this problem? Luckily, this has been already studied a long time ago. It's nice that it's already in the 80s, people as a solution for this problem. So, and I'm really happy to say that I had the chance to work with both of them, both with Bertero, which proposes basically the idea has been already anticipated, is to substitute a single element detector with a pixelated detector. So Bertero was approaching this point of view from an inverse problem point of view, while Shepard was introducing the pixel assignment concept that has been already introduced by Art. So in the 80s, we already have this solution. So, but it took a lot of years before someone tried to demonstrate it. And in 2010, Enderlein basically did exactly build up a laser scanning microscope in which instead of the single element detector, introduce a camera. Okay, conventional camera. But as I told you before, what happened with a conventional camera, this is kilohertz. Okay, so you have a frame in the best case at a millisecond or whatever, but you are scanning so fast. Nowadays with resonance scanner, you approach few tenths of nanosecond pixel per time. Forget that a camera can go so fast. So that means that, okay, it was a nice proof of demonstration, but practically it was just, was a proof of principle demonstration. So in 2013, different groups start to think, okay, we can do pixel reassignment, and I will tell you much better what is pixel reassignment. Well, anyway, I can implement some optical or mechanical strategy to effectively implement this ISM concept. They succeeded, so there are also commercial versions, but still use camera, which are, for me, camera are not really the best system for a laser scanning microscope, because you forget all about the spectroscopy information. So in 2015, Zeiss came out with this Eriscan, which, I mean, I don't know if you know, but it's a bundle of fiber. So it's not a true detector, it's a bundle of fiber connected to different photomultiplier. So ingenious solution, but still not a detector array how we would like to have from the original idea of Bertero and Shepard. So in 2019, we was able to get in our lab this SPAD array detector that I hope that I was able to show you that has all the characteristics to be the perfect pixelated detector. And now I will show you how to use that in the context of image scanning microscopy. So, but first of all, let me explain what is pixel reassignment a bit more in detail and which other method can be used to basically build up an image scanning microscope data image. Okay, so as I told you, basically the scanning microscopy is scanning the probed beam across the sample. And now you don't have for each probed region, for each position of your sample, you end up with a micro images. Okay, so a small 5 by 5 in this case can be 7 by 7, 10 by 10 image of your probed region. Is a true image, this one, okay? But just to make a little bit life easy, so what you can see, we can make a small transformation and think about every single element like a pinhole, okay? So what does it mean? If you think, just forget about all the other pixels, let's consider only this pixel here. So that's a sort of pinhole. Okay, and thereby this detector is able to generate an image, a confocal image, a true confocal image. And since I have 25 detectors that are measuring the light simultaneously, and there is no anymore a pinhole, so I collect all the light. So that's why ISM works, because I don't have to discard the fluorescence. So at the end of the story, I end up with 25 images of the same sample, confocal image of the same sample collected simultaneously. Okay, so I can see this data set as a 4-dimensional data set. I mean, I try to not use math as well. But anyway, so that's, you can see as a collection of micro images or a collection of 25, what we call scanned confocal images. So I have these 25 images. Now what I can do with these 25 images, obviously I would like to have my super resolved images. And what I can do is to try to understand what really this image contain. And to do that, I need to study the point frame function of each images. But as been already anticipated that before, that the point frame function of the confocal microscope is nothing else the product of the illumination point frame function for the detection point frame function in green. Blue is the illumination point frame function, green is the detection point frame function. The excitation point frame function is always the same, because I'm not changing nothing from the point of view of the scanning microscope. What I change is the detection side. So what happens is that every scan image has a different point frame function, which the difference is very basic, because it's the fact that the detection point frame function is shifted for each of these elements. So each element is slightly shifted respect to the other one. So the detection point frame function means that it's shifted. So it's the product of the illumination point frame function for the detection point frame function that is simply shifted by XD, that is the coordinated position of the detector. So 25 images, almost identical, because these are the point frame function of the 25 images. As you see, especially in the center region, all of them are Gaussian function, similar to the one into the center. All of them are confocal microscope. You see in the periphery, they are slightly different. I will tell you something more later. So, and what does it mean having 25 point frame function that are almost identical but shifted in space? It means that basically I have 25 images that are almost identical, but shifted in space, okay? Each detector collects such images that are representing the same object, are very similar, as a similar point frame function, but shifted in space. And if I have 25 images shifted in space and I want to recombine them, what I can do? A very basic operation. So I can do what people call pixel assignment, and is simply taking the images, making autocorrelation function to understand how much they are shifted one respect to each other, and sum them up. So that's a pixel assignment, a very basic operation that the computer can do in a fraction of of a millisecond. So that's a sort of instantaneous reconstruction. So as you see here, so what happened when I take the 25 points per function and I basically, if I take only the one into the center, that's the ideal confocal in which you have a good resolution. So this is the full ideal maximum, but a poor signal to noise ratio because I throw away all this light around. If I sum them up, that's what happened. I collect all the light. So if I open basically the pinhole, I collect all the light, but I'm losing in resolution. So if you remember, the resolution depends by the size of the pinhole. But if I make this pixel assignment operation, what happens? I end up with a resolution that is even better of the one of the confocal somehow. So maybe the true ideal confocal is ISM because it's even better than, I'm joking, obviously. But with high signal to noise ratio. Okay. So some example really fast. So these are nothing exotic, tubulin, nectar tubulin, so closed pinhole. You can see that it's very noisy, the image. If I open the pinhole, I get a lot of signal, but basically I lose in resolution. If I apply adaptive pixel assignment or anyway pixel assignment, then I end up with a super high signal to noise ratio and twice the resolution. This is also visible here. If I plot this intensity profile, you clearly see that the red curve that is image scanning microscopy allow you to better resolve this dip that is that tell you that this tubulin, these two filaments are separate. Okay, but I mean, as I told you, I came from computer science. I don't want to use too much math, but there are much better approaches to reconstruct. Maybe they are not online in real time, but for sure provide better results. One is to dig into multi-image deconvolution or inverse problem. So very fast, but why it should work better? Because pixel assignment basically assume that all the point per function are the same, but this is not true for the peripheral one. So in the case of the convolution, I can take into account this information because I use the true points per function of my system. And what I'm doing really fast, I'm using a statistical approach for which I need to basically, I consider every measurement, every pixel or every scanning image as a realization of Poissonian noise, a Poissonian random variable. And I like to stress this point because these are single photon detector array. It's a detector that is only basically the major source of noise, or the only one, is the photon counting noise. Okay, so we are, for those of people working inverse problem, so there is a lot of theory about Poissonian statistics, but really a few applications where to apply, and that's one of them. So anyway, I derive, basically I use a maximum likelihood approach, so I need to derive the likelihood function and then optimize this likelihood function, find basically the image, the object that best match the image that I got from my microscope. Long story short, so let's go to the result. As you can see, if you compare the multi-image convolution compared to adaptive pixel assignment, you can clearly see that there is the violet curve, there is an enhancement of the contrast of my images. So somehow, if I have time, if I can, I mean, we are talking about icon, not a life, I can process the data in a much better way. What is a little bit of advertisement somehow. What is nice of this technique is similar to RIM. Somehow you don't have to do any change in your sample preparation. So you are still using the sample preparation that you use for a confocal that has been said before is one of the most used techniques. So that's an example again in tubulin. That's an example of static chromatin compaction. You see the enhancement in resolution. You can also move to deeper as much a confocal microscope can go deeper because of optic aberration and go into tissue. So it's still preserve all the characteristics of a confocal microscope, but you get this twice resolution enhancement, a high signal to noise ratio. So again, why is important high signal to noise ratio? Not to get better image, but to reduce the laser power. So that means that this technique is much gentle with your live cell imaging. And okay, wow, so far so good. Not really. And now I came to the point that that I anticipate. So as I told you before, basically what you do, you open the pinhole to collect as much as possible light, because you don't want to lose in signal to noise ratio. But if you open a pinhole, you also collect autofocus light, because the reason of the pinhole was to reject autofocus light. So that's the reason why at the beginning, this was somehow quite underestimated. So if you want to really get a benefit from image scanning microscopy, you still need to have a pinhole. Typically you set to 1 area unit, which is okay to get good optical sectioning, not the best optical sectioning, but to collect as much as possible light. So yeah, basically ISM was simply moving a sort of balance between lateral resolution and signal to noise ratio to a new balance between optical section and signal to noise ratio. So it was not really a true solution. But what is interesting is that that's very similar to how we explain optical sectioning, is the fact that the micro images, if you remember, for each position of my sample, I collect the micro images, are encoding some information about the axial position. So because if you defocus your sample, that's a simulation, you see that the pattern on your micro image is completely different. So start to be like in focus, very sharp, and then when you go out of focus, it's spread across the sample. So it's clear that there are some axial information about the sample. And that's, I mean, I'm happy, I don't know if it's here, I realized that that's been already studied quite a lot of time before us by Giuseppe, so which implemented something similar. So, but anyway, so there is, this information are there. How we can explore, I don't want to go into detail, but I can modify my multi-image deconvolution in order to consider that this is a three-dimensional object. So we are not interested in flat object, we are interested in 3D. We reformulate the problem, and now what we ask to the problem, what we ask, which is the solution that we would like? We would like to simply remove out-of-focus light. So basically to generate two focal plane, one that contains my in-focus image, and the other one that contains the out-of-focus image. So I want to recover basically the optical section. So again, I will not go into detail of the algorithm, I just want to show some results. That's again tubulin network. So that's the image of a confocal microscope when I open the pinhole. And that's the image that I got when I start to apply multi-image deconvolution with this enhancement optical section. So we call S-square ISM. So, and that's the part of Signa that we remove. So you see, you are able really to remove the autofocus light. So I can say that now effectively you have a system that gives you twice of the resolution of a conventional microscope, so are reaching the ideal resolution of a confocal microscope, keeping signal to noise ratio high and keeping also the optical sectioning. So that's another example. I mean, here I want to highlight that when your sample is very thin, basically there is no difference. Apply adaptive pixel assignment or multi-image deconvolution, but when the sample becomes thick, it's clear that I get much optical sectioning when I apply this square ISM algorithm. That's another example. So these are mitochondria. So as you can see here, this region mitochondria start to be a quite complex, much complex than the cytoskeleton environment, because you have quite large structure in the order of sometimes also a few hundred of nanometer up to micrometer. And you can clearly see that here, I cannot distinguish nothing, mainly because there is a lot of autofocus light, not because maybe the resolution is not good. So, but when I apply this new algorithm, I'm able to resolve completely the structure of the mitochondria and remove what is very important, all the autofocus background. So, yeah, since, how much time I have? Okay, good. Yeah, since I'm, as been mentioned about SPAD microscopy, that was a sort of my previous life. Obviously, we tried to combine this system with SPAD microscopy. I have to be honest, the expectation was a little bit poor. It was not really satisfying in the sense that somehow, if you apply to SPAD microscopy, ISM is useless. In the sense that, I mean, SPAD microscopy work by sharpening the excitation point function, and thereby the concept of ISM basically fail very, very fast. When you increase the intensity of the laser, there is no anymore enhancement. But still, it is very important because what you do, you can remove autofocus light, which is something that in SPAD microscopy is even more prominent because the autofocus light can be generated also by your SPAD beam. So that means that it's a nice combination with SPAD microscopy when you want to remove autofocus light excited by the excitation beam or by the SPAD beam. Okay, we skip completely this part because I don't know, I mean, just a flavor of this part. Otherwise, does not make sense to speak about photo-resolved microscopy. So now, as I show you, it's basically ISM basically use only the spatial information provided by the detector. But as I told you, this detector provides also temporal information, and specifically is able to measure what is called the photon arrival time of the microscope respect to an excitation pulse, and thereby is able to measure the Frei's lifetime of your sample. And fluorescence lifetime is a spectroscopy technique that can combine structural imaging with functional imaging, because by measuring the fluorescence lifetime of your probe, you are also able to say something about the environment of the probe. For example, about the pH in which the probe is located, or the ion or oxygen concentration, or even better, some interaction with other molecules. So it's becoming really popular because it's able to combine structural information, in this case super resolved, because we combine with SIM, with some functional information. So this is a basic example in which we use, for example, this polarity sensitive membrane ANEP probe to measure when the membrane is ordered or where the membrane is disordered. So fluorescence lifetime is able to reveal this type of configuration of your membrane. Another nice aspect, okay, everything obviously can be done in live, as I told you before. That's the same experiment on the membrane, okay, but in a live cell. As you see, the color in this case, this map denoted the intensity, this map denoted the fluorescence lifetime. As you see, there is some change in color, which means that the membrane is in a different order. Another important aspect that we can use lifetime to make multi-target imaging. So fluorophore has a different lifetime. Even if they have same emission spectra or excitation spectra, they show different fluorescence lifetime. Thereby, we can implement basically a very simple system, one single laser, one single detection to have multi-target imaging. I will skip all the part of the dynamics because I want just to go to the end. And yeah, I mean, as I told you, I just showed a little bit the tip of the iceberg of the use of this new concept, or also the new use of this new technology that is the SPAD array. So if you are interested, there is all this our literature. More recently, we also move into the field of single molecule and single particle tracking. So, and because effectively this detector can be beneficial, for example, when combined with mean flux or when combined with real-time single particle tracking. But let me go to one of the, to my opinion, one of the most important slides. Is the fact that we really trust on this technology as a sort of new paradigm for microscopy. And thereby we want to disseminate as much as possible. So I already anticipate you that we develop our custom data time tagging data acquisition system. We publish it under open source regime. So if you have some electronic guy in your lab, you can download everything. This card is a development kit that costs few thousand of euro. Now we are working on a version that is few hundred of euro, so really cheap compared. So we are building our microscope control software. So again, that's an open source software. You can download it. You work with National Instrument Board. If you already have in your lab, you can use it. We are working on something also in this direction to remove also the National Instrument Board. We provide, okay, so that's an in progress project. So we are trying to provide you all the instruction also to build up your custom photo-resolved microscope using, in this case, Thorlab's component, and also thanks to the support of Genoa instrument. And also we have implemented a series of Python library to analyze the data, both ISM and lifetime. Some of them are in NAPARI because we believe that is growing and it makes sense to implement for this platform. And yeah, with this, I want just to thank you. I want to recommend these two workshops from Andrea Bucci and Lauren Lee, which they will try to explain a little bit how to build this type of microscope. And so thanks to the funding agency and thanks for your attention.
Oh, thanks. I'm just curious, it's a really great presentation, a really elegant idea. How much signal-to-noise ratio improvement do you get versus the Aries scan? Because I guess the Aries scan also is doing this simultaneous off-axis point spread function collection.
Theoretically, the signal-to-noise ratio enhancement that you get is given by the ESM technique, so thereby is the same. So, I mean, thinking about the Aries scan using the same size of our SPAD array will be the same. The theory is the same one. Then there is the technology. The technology means how sensitive is the detector. I can tell you any single data about my detector. I'm happy to discuss in detail. I don't know so much about Eriscan because it's a company that typically I don't say. That's a fiber bundle. So, but from the theoretical point of view, it's the same. But the sensitivity of the detector is different, and thereby is different, the final signal-to-noise ratio.